Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about micro-instructions. At the end of this video, the student will gain knowledge regarding what is control memory, how the microprogram can be executed, what is micro-instruction, what is the format of micro-instruction. The basic agenda of this video is the introduction, micro-instruction format, types and examples. So here the instruction set architecture will provide various layers of abstraction. So here the basic layers of abstraction are: the user can give the program to the computer. This program can be converted into machine language by using either compiler or interpreter. If at all in case of assembly language, the assembly language program can be converted into machine code with the help of assembler. And this code can be understood by the computer, and it has to activate the necessary hardware units in order to execute and to provide the required functionality to the user. Until the high-level language that can be converted into low-level language, the software part is the user perception, and below that the hardware components can be active in order to provide the required functionality to the user. So here the instruction set architecture is act as an interface between this software perception of the user and the hardware perception of the user. If the user given an application and can given a task by using the sample application Netscape Navigator and the operating system, and here this application the task can be converted into the machine form in case of high level languages by using the compilers, and in case of assembly language by using the assembler. The object code has to be created, and here after conversion the processor memory IO subsystem and dispatch the control so that the necessary digital design, the circuit design, transistors can get activated to execute the task that is supplied by the user. The top part from the instruction set architecture is the software, and the bottom part is from the instruction set architecture is the hardware. The hardware deals with the physical components of the computer. So here the instruction set architecture, it acts as an interface between this software and the hardware components of the computer. An instruction set architecture is part of abstract model of the computer that defines how the CPU controlled by the software. Not only this, through this instruction set architecture, the instruction set architecture defines what is the memory model, what is the instruction format, and what are the registers and various types of addressing modes. The ISA acts as an interface between the hardware and the software, specifying both what the processor is capable of doing as well as how to get it done. So this is the instruction set architecture, and it can act as an interface between software and hardware, and it is also specifies the basic memory models and instruction format, addressing modes, and what are the operand register. But what is the architectural basis for the programming? Programs are written by humans, typically use the high-level languages to express the logic. And the high-level languages facilitates the natural language. So with the help of high-level language, the user can specify the basic logic in the program. Programmers learn to use language based on expressiveness and ease of use. The high-level languages facilitates the readability so that the programmer can be easily express and he can easily operate and compose the program. Language designers are not limited by imagination in developing new operations and techniques, but too much complexity present real difficulties for practical and widespread uses. So the high-level languages facilitates the readability as well as ease of using the language, debugging it, and all facilities can has to be provided with the high-level language. When going downwards to the machine language, it increases the complexity for the user, but the machine can directly understand it so that the speed of execution of this machine code can be high. So if user have complexity in coding, then the user feels difficult to write the programs. That's why the high-level languages supports the natural language so that the user can easily code it and execute the program. A computer instruction sets are limited by the complexities of working with materials on a micro and nano scale of fabrication. The instruction set facilitates the complexities and how the fundamental physical applied signals to electromagnetic properties of the matter. Optimal design of complicated circuits with well-proposed input-output logic. So here the instruction set can facilitate how input-output can be supplied to the programs and how computational processing can be done with various micro operations. So performance and timing considerations can be considered and many other practical theoretical objectives can be considered in the instruction set so that the user can easily frame the microprogram for the intended task. What is micro operation? In computer central processing unit, micro operations are detailed low-level instructions. So what operation can has to be performed can be specified with the help of micro operations. A micro instruction is a symbolic microprogram can be translated into binary equivalent by means of assembler. Each of assembly language microprogram defines a symbolic micro instructions. So collection of symbolic micro instruction is the microprogram. Each symbolic micro instruction is divided into 5 fields: label, micro operation, the condition, the branching, and the address. So by using this format, the micro instruction can be specified in the assembly language. What is microprogram? A sequence of micro instructions constitutes a microprogram. And the collection of micro instructions is a microprogram and can be executed one after another in a sequence. The use of microprogram involves planning all control variables and how the task has to be performed. Those tasks can has to be written in a sequence pattern. The content of the word in the RAM at a given address specifies the micro instruction. What is microcode? Micro instructions can be saved by employing subroutines that use common section of microcode. Whenever a subroutine is occurred in the microprogram, the microprogram suspends the execution of the current program and it has to serve the subroutine and the statements that are specified in the subroutine can get executed in a sequence until the return statement. Whenever a return statement is identified, it has to resumes back the main microprogram execution. So a computer that employs a microprogrammed control unit will have two separate memories. One is the main memory, second one is control memory. A memory that is part of the control unit is referred as the control memory. Control memory holds fixed microprogram consists of microinstructions that specify various internal control signals for execution of register micro operations. Microinstructions are stored in control memory in groups. Each group specifies a routine. How these two memories can be arranged in the microprogram computer. So here two memories, one is the main memory, second one is the control memory. Here this is the location of the main memory. The second one is the control memory. Control memory, the memory associated with the control unit. And this memory can be accessed, the control memory can be accessed with the help of CAR control address register. And the subroutine address can be saved and with the help of the subroutine register. During subroutine calls, the written address can be stored in the subroutine register. And the main memory can be accessed with the address register. When there is an interrupt can occur, the written address is stored in the program counter PC. And the data register holds the data and the address register holds the location of the respective memory where this data is written or read from. And this multiplexer is used to select either the main memory or the control memory. The address in the main memory can be accessed with the help of address register, and what is the data at that address can be transmitted to the data register. This data register value can be considered in the arithmetic logic unit for the processing along with the accumulator. In case of the instruction belonging to the control memory, with the help of CAR register, the data can be fetched into the data register and can be used in the arithmetic and logical unit along with the accumulator. So this is the structure of the two memories in the microprogram. What is microinstruction format? A microinstruction format consists of 20 bits in total. So here how these 20 bits can be arranged. So here the total length of this microinstruction is 20 bits. And here three micro operation fields are there, F1, F2, F3. And each field is of 3 bits length. So F1 is of 3 bits, F2 3 bits, F3 3 bits. These are used to specify the micro operation. So what operation has to be performed is specified with the help of these fields F1, F2, F3, each occupy 3 bits. Next is 2 bits that is specified with the CD. So CD is the condition for branching. The branching can be two types, conditional branching or unconditional branching. Conditional branching means before branching to the specific location, the condition can be checked. If the condition satisfied, then only the branching can be take place. Unconditional means without checking the condition, the branching can be take place. In case of conditional branching, the CD field can be considered. The CD is condition for branching. They choose the status bit conditions. How the conditions can be checked means based on the status registers which is having the status bits like carry, 0, overflow. Based on these bit values, the condition can be checked. And the CD can have 2 bits length. Next one is BR. BR is the branch field. It determines the type of branch. And BR is also occupies the 2 bits. Next 7 bits can be specified. The AD address. AD is the address field. It includes the address field whose length is 7 bit. The micro operations are divided into 3 fields of 3 bits each and 2 fields of 2 bits each and 7 bits to specify the address. So this is the micro instruction format. Now we will look into how this field 1, field 2, field 3 can be used for micro operations. So here this is the microprogram sequencer of the control unit. Here the control memory can be accessed with the help of CAR register, control address register. And this is the control memory where the micro instructions can be stored. The format of the micro instruction can be the 3 fields of the micro operations F1, F2, F3 and next the CD field, next the BR field of 2 bits each and the 7 bits address. So here in the control memory the micro instruction format can be used and this control memory can be accessed with the help of control address register. So here the microprogram sequencer generally performs the 4 steps. One is the incrementation that can be performed with the help of incrementer. The incrementer can increment the CAR value by 1. The second step is branching. The branching can be done with the branch logic with the help of mux2. And here if at all conditional branching, the test can be performed. If condition or test is satisfied, then only the branching can be take place. Next task performed is the address mapping. So here the address can be the instruction, the program is collection of instruction. Each instruction can be fetched into the instruction register in order to execute the program. This instruction register address can be mapped to the CAR address with the mapping logic. And here the opcode of the instruction can be copied directly and this opcode can be preceded with 2 zeros and followed by 1 zero in order to map to the control address register. The address mapping can be done with the mux1. Next, subroutine call. Next step is the subroutine call. The subroutine call can be facilitated with the help of SBR, subroutine register. The return address of the program subroutine can be stored in the subroutine register. So in this way, the microprogram sequencer can perform 4 steps. One is the incrementer of the CAR value. Next, the second one is branching. Third one is address mapping. Fourth one is subroutine call. So here the micro instruction field descriptor 1. So the micro operations can be divided into 3 fields F1, F2, F3. So what is the F1? F1 consists of occupies 3 bits. So with the 3 bits the user can able to perform the 8 micro operations with a bit sequence of 000 to 111. So what are the micro operations that can be specified in the field 1? If at all F1 can consist of 000, none operation, NOP, no operation can be taken place. If the field 1 consists of 001, then add micro operation can be performed. During that time, the data register value can be added with the accumulator value and the result is stored in the accumulator itself. In case of F1 consists of 0, 1, 0, CLR AC, clear AC. AC is loaded with the initialized with the 0 value. In case of F1 consists of 0, 1, 1, then INC AC, that is increment accumulator. Accumulator value can be incremented by 1 and the result is stored in the accumulator. In case F1 consists of 1, 0, 0, then DR2 AC. So here the data transfer can be taken place from the DR register to the AC register. So DR register value can be moved to the accumulator register. Next field is 101. During this 101 F1 value, DR to AR data transfer can be occurred. So DR in the data register 0 to 10 bits can be moved to the address register AR. Next, if the field F1 is consists of 110, then PC to AR data transfer can be taken place. So here the value in the PC can be moved to the AR register. If at all field 1 consists of 111, then memory write operation can be performed. The value, the content of the data register can be transferred to the memory location that is specified by the AR register. So these are the 8 micro operations that can be specified with the help of field 1. Similarly, we are having F1, F2, F3, each of 3 bits size. So the F1 can support these 8 micro operations, F2 8 micro operations, F3 8 micro operation, total 24 micro operations. So here, what are the operations that can be specified with the F2? If the F2 consists of 000, then no operation NOP, and if at all F2 contains 001, then the subtraction micro operation can be performed. The accumulator, the data register value can be subtracted from the accumulator value and the result can be saved in the accumulator. If at all F2 consists of 010, then OR logical operation can be performed. Between the data register content and the accumulator content, the OR logical operation can be performed and the result is stored in the accumulator. If the F2 consists of 011, then AND logical operation can be performed between the data register and the accumulator, and the resultant value can be stored in the accumulator. If F2 consists of 100, then memory read operation can be performed. The address pointed by address register, the content from the memory is fetched and this can be transferred to the data register. Next, if F2 consists of 101, then accumulator to data register data transfer can be occurred. The value of accumulator is transferred to the data register. In case of F2 consists of 110, increment the data register. Data register value is incremented by 1. If F2 consists of 111, then PC to DR operation can be done. So the PC value can be transmitted to the DR 0 to 10 bits. So these are the 8 micro operations that are supported by the F2 bit. Now we have to look into the F3 bit. So the micro operations that can be specified during the F3 bit are, if at all F3 is 000, then no operation is performed. When F3 contains 001, exclusive OR operation can be performed on the data register and the accumulator register. If 010 is controlled by F3, then complement operation can be performed. The ones complement of accumulator can be stored in the accumulator. Next, 0111 F3 value can be used to perform the left shift operation. So, shift left operation can be performed on the accumulator and the result is stored in the accumulator. If F3 contains 100, then shift right operation is performed on the accumulator. Result is stored in the accumulator. F3 contains 101, then INC PC increment the PC value by 1. F3 contains 110, then AR to PC data transfer can be occurred. The content of address register is moved to the program counter. 111 is reserved. So these are the micro operations that is specified with the help of F1, F2, F3 fields of the micro instruction, and these fields can occupy 3 bits each. The later on CD and BR are used and each can occupy 2 bits size. Now, how these F1, F2, F3 operations can specify the micro operations. Suppose that a given micro instructions specify 2 simultaneous micro operations from F2, F3 and none from the F1. So here the F2, F3 are specifying the operations, 2 simultaneous operations, but F1 is no operation. So here F2 is 100 and it is moving the address, that is memory content that is specified in the AR register to the DR register. So here read operation, memory read operation is performed with F2 value is 100. The second simultaneous operation is incrementation of PC value. PC value can be added or incremented by 1 and the result is shifted to the PC with F3 of 101. How the bits of the micro operation can be specified is F1 is no operation, so it can be 000, and F2 is 100 to initiate the memory read operation. Next, F3 is increment INC PC, so it is 101. So like that, the F1, F2, F3 can be used to specify the micro operations. Next field is in the micro instruction format is the condition field. So the condition field is of 2 bits. So here the possible combination of 4 possible combinations we can check with the condition field. When the CD field contains 00, then the condition is always 1. So unconditional branch. So unconditional branch means without testing the condition, the branch can be take place. So here always the condition value can be 1. Why? Because it is a unconditional branch. When CD is 01, the indirect address bit has to be taken place in the instruction format. The MSB can specify the I value. If I value is 1 means it is indirect address. So here the data register 15 with the I bit can be set to 1 so that it can be point to the indirect address. And if condition field consists of 10, then accumulator 15th bit, that is the sign bit of the accumulator, and that sign bit can be operated. If sign bit is 0 means it indicates a positive value, and if sign bit is 1 means it indicates a negative value. And if condition field consists of 111, then accumulator is equal to 0. The Z status bit can be checked here, 0 value in the AC. So these are the 4 possible conditions that can be verified with the help of condition field CD and consists of 2 bits length. Next is the branch field, BR field, and it is also of 2 bits length. So when branch field consists of 00, jump instruction can be, micro operation can be taken place. So here the address can be moved to the CAR control address register if condition is equal to 1. If condition is 0, CAR plus 1 value can be moved to the CAR. So here why the jump operation can be used to transfer the control, current program control to the specific label, and from that onwards the program can be executed. For example, here in the program a label is there. For example, the label name is test, and from this the micro operations, the assembly language program is there. And here if it all a statement JMP test is there, then the program can transfers. Generally the program can be executed one micro operation after another in a sequence. When it identifies the jump, what is the label specified, to that the control can be transferred, and again from that label the program can be continued execution in a sequence. When branch instruction BR can contains the 01, call operation can be, micro operation can be take place. The call can be used to call the subroutine. So here when the subroutine is called, the address, the return address can be saved in the subroutine register. So CAR plus 1 value can be saved in the SBR. So and the address can be moved to the CAR if the condition is 1. Why? Because the specific subroutine, the program control has to be transferred. When it find the return, then with the help of SBR, the main program execution can be resumed. So CAR plus 1 if condition is 0. So whenever a call statement encountered, then the return address can be moved to the SBR and the address can be moved to the CAR in order to execute the subroutine. When the BR field contains the 10, RET return statement can be observed. So the SBR, the return address that is saved during the call statement, can be moved to the CAR. Next, whenever branch consists of 11, map, address mapping can be done. So here the CAR 016 can be, the control address register 016 fields can be 0, and the DR 11 to 14 can be moved to the CAR 2 to 5. So here the opcode of the address register can be copied directly to the CAR with preceded 2 zeros followed by 1 0, so that the address mapping logic can be implemented in case of BR is 1 1. So in the micro instruction format, the three fields are F1, F2, F3, which is used to specify the micro operation is of 3 bits length, and next 2 fields are condition and branching, which are occupying 2 bits length, and next the 7 bits are used to specify the address. And what are the types of micro instruction formats? There are basically 3 types of micro instruction formats. One is horizontal format called horizontal microcode. Second one is vertical format called vertical microcode. Third one is field encoded format. Each of these formats provide a trade-off in terms of control store size and speed of operation of the control unit. Now, what are the 3 different types and how they can be used to control the speed of execution of the microprogram? The first one is horizontal micro instruction format. So in the horizontal micro instruction format, Each control signal is represented by a single bit in the control word. So thus, if the design has 500 control signals, 500 bits in the control word. So that is the format of the horizontal micro instruction. But here the disadvantage is the size of the control store is very large. So here how the horizontal micro instructions can be done. So individual control signals from the system bus can be carried out. If it all jump instructions are there, the control can be transferred to the specific labels. So this is the micro instruction branch. Individual control signals are used. So how many control signals are there? That many control words can be there in the horizontal micro instruction. So the size is the disadvantage in case of horizontal micro instruction. Next is vertical micro instruction format. So in order to execute this code organization, vertical microcode organization, so first identify number of distinct control words in the design. So here how many control words distinct are there in the control words? First identify it. Encode is a distinct control word by assigning a unique n bit code to it. So and if it all n control words are there, log 2 of words can be present in the micro instruction. Instead of storing the actual control signal that need to be generated, only n bit code is stored for each control word. And use n by 2n decoder to generate a decoded signal for each distinct control word. To generate the control signals, use OR gate based on the decoded control word signals for each control signal in the control design. So how the vertical micro instruction can be executed. So here first step we have to identify how many distinct instructions are there. For those instructions we have to use the decoder to decode the instruction code in order to perform the micro instructions. But in horizontal micro instructions, one signal, one control word can be present. But in case of vertical micro instruction, the size can be reduced by identifying and grouping the distinct micro instructions and using a decoder in order to get the micro operation. Next, third variety is field encoded micro instruction format. It can be observed that there are signals in the design that cannot be one at the same time. So the signal can be 0 or 1. These signals are called mutually exclusive signals. In order to save the size of control store, all mutually exclusive signals can be grouped together and encoded. So here, mutually exclusive fashion, the micro operations can be executed. So here, the mutual exclusion signals can be grouped as one and can be encoded in the field encoded micro instruction format. So here demultiplexer can be used, the micro operations which can be applied on the one, those can be decoded here. Remaining are the one-to-one individual control signals can be executed. So in short, field encoded micro instruction can be combination of vertical and horizontal micro instruction formats. So these are the three types of micro instruction formats. And we have to look into what is symbolic micro instruction. So each line of assembly language microprogram defines a symbolic micro instruction. So here we are having 5 fields to specify the micro instruction: the label, the micro operation, CDBR, and the address. The label field can be empty, or it can specify symbolic address. So here the label can be defined any user defined name and can be terminated with a colon. So this label can be generally used in the jump instructions to transfer the control to the specific label. And The next field in the symbolic micro instruction is micro operation. It consists of one or two or three symbols separated by comma. So these may be no more than one symbol in the F field. So here F1, F2, F3, the operations has to be grouped, and depending upon the operation, the group of 3 bits can be represented here. Next is condition field, which can be used to perform the condition checking with the help of status bit values in the status register. So here the sign bit and Z bit, those values can be checked here. So if at all it is unconditional, then U can be 1 and the I value indirect address can be specified with the help of CD. Next, the next field is BR. The BR contains one of 4 symbols which can be used to call, return, and that we discussed in the BR field. Next is the address. The address field specify a value for the address of the micro instruction in one of the 3 possible ways. The first one is with symbolic address. This must appear as the label. Next, second one, with the next to designate the next address in the sequence. When BR field consists of return and map symbols, address field left empty and it is converted to 7 zeros by the assembler. So with the help of this address mapping logic, this address is mapped to the CAR address with the help of the third type of the address operation. So these are the 5 fields that can be used in the micro instruction, symbolic micro instruction. And this is the example. So here this is the micro operation and this is the address fields. So in this way micro instructions can be specified in the assembly language. So assembly language can be collection of the micro instructions. Now consider a problem. A micro instruction format has micro operational fields which is divided into 3 subfields F1, F2, F3, each having 7 distinct micro operations. So each field is specifying 7 distinct micro operations, means each field consists of 3 bits length. Conditional field CD for 4 status bits. Branch field is having 4 operations used in conjunction with address field of ADF. So here CD and BR can specify 4 operations, which means 2 bits of each size can be used for CD and BR. The address space of 128 memory locations. What is the size of micro instruction? So F1, F2, F3, 3 fields can specify 7 micro distinct operations. So they are of 3 bits each. And CD and BR are specifying 4 options. So they are of 2 bits each. And address can be used in order to locate 128 memory locations. 7 bits can be required. So total number of bits required for micro instruction is the sum of all these bits. So it is a 20. Okay. So like that the micro instruction address field bit can be calculated. So in this video I discussed about the what is micro instruction, how it can be stored in the control memory, and what are the fields that are available in the micro instruction, and how they can be used to specify the micro operations, and what are the types of the micro instructions can be discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.